Let me talk about deletion in PA4, because a few people have had a few issues with this. It's definitely the hardest one. And one of the tricks about deletion is you've got a few edge cases to worry about. So we know the general algorithm: find the largest entry in the left subtree, make that the root, right? But there's a few potential complications. So let's just suppose we're deleting the root of this tree, and so there's going to be stuff here on the right which doesn't affect us. But suppose we've got, a case like this. And there could be all kinds of crazy stuff going on. This is the general case. Okay, so we're always deleting the root. So we're going to get rid of this. Okay, so you go into the left subtree. That's this. And we want to find the largest element there. That's going to be the 35. That's going to become the root. Okay, which means 35 is going to take 20 on the left. It's going to take 50 on the right. And then this orphaned left child, 33, that's going to get adopted by 35's parent. Okay, so how do we find this largest element? Well, start off with the left child of the root, right? And just start moving to the right as far as you can. And when you get to a node that has nothing on the right, that's the largest element. The previous node, that's the parent of the largest element, and that's the thing that's going to adopt. Okay, so that's the totally general case, and that one usually isn't too bad. Let me show you one pathological case. So there's a 40, and there's stuff over there, and we've got a 20, and we've got a 10, and you might have other stuff over here, but there's nothing on the right of 20. Okay, so in that case, this is the largest element, right? So we're looking for the largest element in this left subtree, and it's actually this 20. So over here, let's say this is largest, and let's say this is previous, and let's say this is root. Okay, so in this case, what does our code look like? It's something like this. Previous right equals largest left. Okay, that sets up this link here. And then largest left equals root left. And largest right equals root right. So now the largest is adopting all of this on its left and all of this on its right. That's making it the root of the tree. If you want your 5 points for Valgrind happiness, you can free the old root, and then delete always returns the root of the new tree. The new root is L. Okay, so that's the general case. We can't do this code in this case, because in this case probably previous is up here, and if we say something like previous left equals root right, we're going to start getting loops in here. So in this case, here's our largest, here's the root. So largest should be the new root. We don't change anything on its left. It's got a bunch of stuff on the left. We can just leave that as is. Really all we need is largest right should equal root right. So now this is pointing to all of this stuff on the right. Free the old root, return the new root. Okay, there's a third case where your tree looks like this and there's nothing at all on the left. So we don't even have a left subtree we can search to find the largest thing in, because there is no left subtree. And so if this is the root, all we really need is something like temp equals root right. So whatever node is over here, that becomes temp. free R, return temp. So in this one case where there's nothing on the left of the root, you're allowed to just say, okay, the root is just whatever the right child is. So save that somewhere, free the root, return that right child. And that should cover all the possibilities. Sometimes if you've only got one node over here, depending on how you write your code, that might be a special case. But if you write your code just the right way, it's either going to look like this or that. Yeah.
Does it matter if you look at the largest node in the left or right subtree?
Yes. One gets you points, the other doesn't. Okay. If you look at the right subtree, actually you'd need to find the smallest thing in the right subtree.
And you lose points for that?
And you lose points for that, yeah. Okay. But that's a valid way to delete in general, right? Either take the largest from the left or the smallest from the right. But for this assignment, you're required to do the largest from the left.
Okay.
So that's what I'll be looking for. So if you delete and your tree doesn't look like what I expected, and it's really obvious that you did the smallest from the right, you'll lose a few points. If it's not obvious what's going on, it'll just look like delete function doesn't work and you'll lose more points.
I have like one very specific case we inserted that I'd like to ask about.
Okay.
So the very first insertion, we have to allow 0 to be inserted. Normally that's not a problem because after I malloc a new structure, the very next assignment is to put data into there. But the initial node that starts when you first run the program is initialized to 0. And so now everything goes sorted against that initial 0. So
is this for the tree?
Yeah.
So there is no initial node. An empty tree is just null. There's no sentinel.
Okay, yeah. Well, I mean, I'm not like mallocing a sentinel, which is why it's weird. But for some reason, when it looks at the address of the original, the very first one, because everything gets initialized, has 0 as the integer, and then when it compares everything against it.
But you'd only be mallocing when you're actually inserting some number, right?
Yeah, so
if you're inserting 50, you're going to malloc, you're going to set the data to 50.
So that's the interesting thing, is that I'm not telling it to malloc anywhere in the main program, but the very first time it runs and it's past the address of the structure, it starts saying like, okay, there's a 0 here.
The address will be 0, but if you try to look at the data, it should segfault.
It's not segfaulting.
Interesting.
The address is 0. Because my very first thing is to check whether or not the address is 0.
Interesting.
Now I'll just show you after class then.
Yeah.
I think there's a lot of people.
There are a lot of people going to show me things after class. But we'll see how that works. Okay, that's interesting. All right, does this help at all? Yeah.
I have one question. It's more of a simple one. So when you're printing like LNR and so all those in the recursive loop, so you probably print the number and then the comma. So then you get the last comma at the end. How do you get rid of that last comma?
Did I say to make them comma separated?
Yep.
Oh, that's mean. So we can be stateful. So set a flag. Yeah. and it's one of the cases where an evil global is actually a good thing to do. So you can have a flag called, first print. Set it equal to 1. And then inside your traversal code, right, so set this before you call, say, LNR. Right, so set that to 1 and then say LNR tree. And then in your LNR code, if first print is not equal to 1, print a comma, and then go ahead and print your number out. And also set first print equal to 0. So the first time that you go into your LNR code and you're about to print something, it'll say, is first print 1? Yes, it is, so it won't print a comma. But it'll also clear that flag. And then you print your number. So your first number comes out without a comma before it. But then the next time that you're going to do a print, so you recursively called LNR, it's going to say, is first print 0? Yes, it is, so I'm going to print a comma. So that's probably the easiest way to do it. And like I say, that's one case where a global, at least global to the LNR stuff kind of makes sense. You can pass a variable, but it kind of defeats the recursion mechanism to do that, because recursion's trying to keep everything local. I occasionally have students who, at the end of their traversal code, they just print a backspace and a space to erase that comma.
I tried to do that, but I couldn't.
You can print a character 8 to get it to go back one spot.
You have
But
to print a character what?
8?
8?
Yeah, like if you print a %C and for the argument you pass it an 8, or I think a \b maybe is also a backspace.
I was using
Backspace B.
Yeah.
Yeah.
B, and I couldn't get it to work.
Okay,
Maybe it's the 8.
but this is a better way.
That's easier.
Yeah. All right, other questions? Yeah.
So at my search function,
Mm-hmm.
but I cannot figure out how I would go about printing it out, whether the number's been found or not.
What does your search function return?
It
Anything?
just returns the root. Like I set up with the struct node, like the add and the, so I can't put like a flag for 1 that gives me 1.
Oh, so you can define your search to return, say, an integer.
Oh, so I can make it an image. Okay.
You can make that return an int.
All you have to do is a struct node, like the delete and the add function.
Yeah, so we're not modifying anything here, we're just examining the tree.
Okay, well, I can do it like that. That was the big thing.
Okay.
I would try to return like a 1 or 0.
Yeah.
Give me a warning and change
Yeah,
it.
if you're telling it it's a pointer, it'll complain.
Yeah.
So yeah, just have it return an int, and then if the root matches, return 1. Otherwise, return what you get by searching either the left or the right.
Okay.
Cool. Yeah.
I probably messed up huge in my code, but I don't exactly know where, because I wrote my insert and my search function, and I wanted to test to see if a number was in the tree. But say I insert a single number, and then I try to search for other numbers that wasn't that number. Every number after that says it found it. I don't know why that happens.
Interesting. So if you go through GDB, you should be able to see where it's making that decision that it found it. Right, where it's actually returning a 1, and that might tell you what's going on.
Yeah.
You might have an equals instead of an equal somewhere.
Nope.
Nope, okay. That would be the easiest one to fix. Yeah, so I mean the algorithm, if it matches the root, return 1. If it's less than the root, return what search gives you.
Yeah.
Right? If it's bigger than the root, return what search returns on the right. But also make sure you check to see if the tree is null.
Yep.
And if it's null, return a 0.
Yep.
Sounds good.
Maybe it's my insert function. I don't know.
Okay. Well, you were first in line to see me after class, so
Oh, okay.
so you can do that. All right. Other questions? So breadth first traversal, right? Remember your queue should be storing pointers to tree nodes. And so if you grabbed your PA3 code, you have to tweak it a little bit, make sure it's inserting pointers to tree nodes, it's returning pointers to tree nodes in your remove function. And that's been the main thing I've seen with people is they're returning a pointer to a queue node, or they're returning an integer or something like that. So your queue node stores a pointer to a tree node as its data. All right, well let's wrap up heaps. So you can up heap, you can down heap, you can heapify. That's everything there is to know about heap algorithms, basically. right? Pull off the root, move the last element up, down heap, or add something to the last element and up heap to insert. So let's look at implementation. So I'm just going to make a little heap here, and I hinted that we're going to store this in an array. And I'm going to start with the first node. I'm going to store at location 1. I'm not going to use location 0. So we're just going to store these things sequentially. I skipped D. I can't believe I did that. All right, A, B, C, D, E, F. And we're going to have something that tells us the index of the last node in our heap. So what are the main things we have to do when we're working with heaps? We need to find the root. Where's the root in this array? What location in the array? All right, so the root is always, so here's our heap. The root always is element 1 in the heap. So we don't have to do any searching. That's always easy to find. What's the last element, the rightmost element on the bottom row in this heap? Yeah, it's the element stored at position last. So heap bracket last. That's the last element. So F in this case. So if we want to insert another element into our heap, where does it go? It just goes at heap bracket last plus 1. So if I want to add something to the heap, the first thing we do is we put it at the last element, the rightmost element on the bottom row. That's just going to say increment last and store it at that location. And if we want to remove the rightmost element on the bottom row, we just grab the element at location last and we decrement last. So these are single operations, right, for grabbing the root, grabbing the last element, putting something in the last element, removing the last element. So what about lineage? So here's a node. Here's its index. Here's a left child and its index. Here's a right child and its index. And I'm going to put down a parent and its index. So let's start with node A, index 1. What's the index of, what's its left child? Left child of A. Oh, you can't read my mind? Okay. That would be like tricky to make a good exam if you could read my mind. Alright, so what's the left child of A? Left child of A is B. Right child of A is C. What's the index of B? Alright, index of C is 3, and A doesn't have a parent because it's the root. Alright, how about node B? That's index 2. What's its left child? D, which is 4, and what's its right child? E, which is 5. Okay, and let's just do one more. Let's do C. So that's index 3. What's its left child? F, which has an index of 6. Oh, what the heck, we'll go crazy. We'll put an extra node there. So its right child is G, which is 7. Do you see any pattern between a node and a node's index and its left child's index? Yeah. For any node, if you know its index, multiply by 2, you get the index of the left child. And if you multiply by 2 and add 1, you get the index of the right child. So now we got a way to move down the tree. Left child equals 2 times parent. Right child equals 2 times parent plus 1. Or left child plus 1. So we don't need pointers to move around this structure. If we start with root 1, we know its children have addresses 2 and 3. If we want the right child of 3, it's going to be 7. If we want the left child of 7, it's going to be 14. If we want the right child of 14, it's going to be 28 plus 1 is 29. So real simple formulas, either 2x or 2x plus 1, lets us move down one level in the tree. And that's half the game in playing with heaps, is looking at your children. So if you're at node I, you compare your value to the values at 2i and 2i plus 1. If you're down heaping, you see if you're bigger than both of those, and if you are, you're done. If not, you take the largest one, you swap those 2 entries, and then you move to that index and you keep going. Okay, node B has a parent of 1. Parent is A. Node C has a parent of A, which is also 1. Any guesses how you find your parent? If you know your index, how do you find the index of your parent?
Do you know if you're the right child?
No, you don't. If you did, what would you do?
Wouldn't you just do like back solve it for?
Yeah. So if you're a left child, your parent is just your ID divided by 2, your index divided by 2. If you're a right child, your parent is your index minus 1 divided by 2. And right children are always odd. Left children are always even. So it turns out
You can figure it out.
if you do an integer divide, your parent's index is always just your index divided by 2. If you're even, that's going to take you exactly to your parent. If you're odd, that's going to round down, and it's going to basically give you your index minus 1 divided by 2. So multiply by 2 to find your children, divide by 2 to find your parent. And if you're doing this on a PIC processor where we don't have multiply and divide, that's not a problem, because we can multiply by 2 by just shifting left 1 bit, and we can do an integer divide by 2 by just shifting right 1 bit.
I was forgetting about that.
Yeah. And that does exactly what we need here. So coding this up, there's no pointers, there's no mallocs, right? You make an initial array, you dump your data into the array, and then you code up the heapify process to turn it into a heap. And heapify, all we're doing is we're looking at nodes, comparing it to their children, moving up and down, finding either our parent or finding one of our children, and the most complex we ever have to do is multiply by 2 or divide by 2, and maybe add 1, and it's just all index math. So this is really fun to code. It's a powerful data structure, but it uses nothing fancier than an array, and that's actually like the most efficient way probably to implement this.
There's no reasonable way to set up a linked list for it.
You could totally. I mean, you can do this with a regular tree. But this question of like finding where the last thing is, right? We can keep a pointer to it. But if we're going to add another node, we need to know sort of what that node's parent was. I saw you try to come by earlier and you chickened out. That's okay.
I need another meter stick.
Oh, I have a hard time finding those in this building, which is surprising. I had a friend who used to work at National Bureau of Standards, which is NIST now, but you know they have like, you know, the kilogram and all this kind of stuff. And there was this running joke because one day they needed a meter stick and nobody could find one. All right, so yeah, you could do this with like a regular tree, but it's tricky to sort of figure out like where the next entry is on the bottom row. You could have back pointers and probably get around it like that, but you end up doing some searching, and it's not clear there's a way to sort of touch up those pointers as you augment the structure. So yeah, this is a really clever way, whoever came up with this. And like I say, it's pretty fun to code, especially after you've been doing pointers for a year, and now you just get to like use an array and some index math. All right, good. All right, let's do something that we did in 215 yesterday. Oh, put this up so I'd remember to mention this. So I posted an announcement. I just want to give a shout out for it. There's a transfer fair today. It's going on right now over at Geyser Hall. And if you're thinking about transferring and you haven't already figured out all the details and dotted the I's and so on, at least this set of schools is supposed to be there. If you have questions about requirements and timing and so on and so forth. And there's probably food somewhere, I would hope. But I don't know. So that's going on till 1 o'clock over in the pub. So you can check them out. So we know about Fibonacci numbers, right? So Fibonacci numbers are this collection of numbers and we get each number by adding the two numbers before it. Right, so 1 plus 1 is 2, 1 plus 2 is 3, 13 plus 21 is 34, and so on. So it's a recurrence relation, so we can define the nth Fibonacci number as either fn minus 1 plus fn minus 2, and this is for n bigger than or equal to 2, or we can say this is equal to 1 for n equals 1 or 0. And so this is a standard recurrence relation. If you're in 215 now, this is what we're talking about tomorrow. And we started it yesterday. So we seed the process for 0 and 1. We say explicitly what the Fibonacci value should be, but then for anything 2 or bigger, we define it in terms of previous values of the Fibonacci series. So the nth term is the n minus first term plus the n minus second term. And so we can write this out by just, adding two numbers to get the next term. And so we can write code to do this. And the code is really 2 lines. So here's the code for finding the nth Fibonacci number. If n is less than or equal to 1, I just return a 1. Otherwise, I return fib of n minus 1 plus fib of n minus 2. So I've got this wired up. Let's do the 11th. Right, so 11th Fibonacci number is 144. That's what we calculated by hand. So this works great, right? And it's really easy to write. We didn't have to make any loops. We didn't have to have 2 temporary variables to keep track of the 2 previous values. We really just used the recursive definition, which is the nth Fibonacci number is the sum of the n minus first and n minus second, unless n is 1 or 0, in which case we just return 1. So the downside to this is even a small task like finding the 60th Fibonacci number is not going to finish. Now we could do this on paper in less than 2 minutes probably, especially if we had a calculator. We just add up, pairs of numbers, 60 times, we'll find the 60th Fibonacci number. And it's not that big a number either. It's not like, you know, zillions of digits. The challenge here is how many times we're recursively calling the Fibonacci function. And so let's just do something modest. Let's just look at fib 11. And these are all the calls that it made. Right, so all of that. So let's, how can we tell how many lines it output? Can we tell how many times it calls itself?
We could add a counter.
We could add a counter with an evil global. What's the laziest way to do this? What?
There's a Unix command.
Yeah, so we can pipe this into word count. Bang, 288 times. Minus 1 time for the answer. So 280 some calls to this function just to calculate the 11th Fibonacci number. So let's try fib 20. $21,892 calls to calculate the 20th Fibonacci number. So this is growing really quickly. And the 20th Fibonacci number is 10,946. What's 10,946 times 2? Someone's got a calculator. $21,892. Hey, that's how many times it called itself recursively. Minus 1. And we saw that up here, the 11th Fibonacci number is 144. The number of recursive calls was 288. So the amount of times that it's calling itself is actually related to the Fibonacci sequence itself, which is either really surprising or not surprising at all. Yeah. So this is a really expensive way to calculate things, but it's so easy to write, right? I mean, it's so tempting to just like do this, because we don't have to think too hard. Okay, so why is this blowing up so much? Suppose we want to calculate the 5th Fibonacci number. To do that, we have to calculate the 4th and the 3rd Fibonacci numbers. To calculate the 3rd Fibonacci number, we have to calculate the 2nd and the 1st. And to calculate the 2nd Fibonacci number, we have to calculate the 1st and the 0th. And these, we don't have to make any recursive call, because our code says if our number is less than or equal to 1, just return a 1. So our recursion ends at this point. Over here, to find F4, we have to find F3 and F2. To find F2, we have to find F1 and F0. And those we don't have to recurse. But to find F3, we have to find F2 and F1, and F2 does F1 and F0. And there's where the recursion ends. So we got 1, 2, 3, 4, 5, 6, 7, a whole bunch of calls to the Fibonacci function. And this tree just gets like wider and deeper as you go. It gets one level deeper, but it gets wide too. But here's something to think about. So we're calculating the 20th Fibonacci number. which requires calculating the 19th and the 18th and the 17th and so on, all the way down to fib 2. And then we call fib 1 and fib 0, and those don't recurse, those just return 1. So now we figured out what fib 2 is, but now we're calling f1 again. Let me do this differently. Let's just do fib 5. So it's calculating 5, 4, 3, 2, 1, 0, and then 1, 2, 1, 0, 3, 2, 1, 0, 1. And that's this tree, 5, 4, 3, 2, 1, 0, 1, 2, 1, 0, 3, 2, 1, 0, 1. Down here it needs to calculate fib of 3. Right, so it's trying to calculate f5, it's got to calculate f4 and f3. So it's about to calculate f3, and to do that it's got to calculate f2 and f1, and calculate f1 and f0, and so on. So to generate fib of 3, it's calling all of these things. But you know, up here, we calculated fib of 3 also. And we calculated fib 2 right here, but we're also calculating it here, and we're also calculating it here. So we're repeating the calculations again and again and again. And that's really the reason why this thing is so inefficient. So to calculate fib 20, we've got to calculate all of these Fibonacci sequences. But, you know, we needed fib 4. We're calculating fib 4 right here. We're calculating it again right here. We're calculating it again right here. So how many times do we calculate fib 4 just to calculate fib 20? All of those times. 1,597 times we're doing the same calculation. Fib 2, we're calculating the same value 4,000 times. So here's an idea. What if the first time we calculate fib 4, we save that value somewhere? And then the next time that we try to calculate fib 4, instead of doing the recursive thing, we'll say, hey, we've already done this. I saved this value for you. Here's what fib 4 is. All right, so I'm going to make an array called saveFib. I'm going to initialize it to zeros. And down here, I'm going to put in an extra statement. So if saveFib bracket n is not equal to 0, I'm just going to return that value. All right, so if we've already calculated this fib value before, we're not going to do any recursive calls. We're just going to return that value that we saved in an array. I guess I can do this if statement first. That's our edge case. Okay. Otherwise, calculate fib n recursively. So I'm not just going to return that value right away, though. I'm going to save it in a temporary variable. And then I'm going to say save this in our save fib array. So I'll save that in our result, and then we'll return result. So I've really added 2 lines of code. Before we do any recursion, I'll see if we've already saved this value, and if we have, I'll just return it. Otherwise, we do our regular recursion, and then we save that calculated result into our array. And the rest of this is basically the same. And there's fib 20. And it made 20 calls going down and then a few calls at the end, and it popped back up. So a total of 40 recursive calls. So fib 30, total of 60 recursive calls. And I can easily do fib 60. The integers will blow up because I need to make like long ints to make them big enough. But it will get an answer really quickly. That might actually be a real answer. So this is a technique called dynamic programming. Dynamic programming works when you have a problem that you can solve pretty easily recursively, and you can solve it by solving smaller problems and putting together those solutions, so something like a divide and conquer. But you have a lot of recurrences of those smaller cases, so where you're frequently re-executing your function at the same values that you've already done before. And in a lot of those cases, if you just code it up as a recursive solution, it'll take a long time to run. But if you throw in this saving of values and reading back values, you can get a solution really quickly. So this is sort of classic dynamic programming applied to Fibonacci numbers. So does the concept make sense? And there's an actual term when we're talking about trees, which is pruning. And what we're doing is we're pruning this tree, right? Once we've calculated F2, we never have to recurse again to figure out F2. So this stuff is never going to happen, and this stuff is not going to happen. And in fact, once we've calculated F3, we don't have to recurse to calculate F3 again. When we make our call to find F3, it's just going to read the value out of the array, and F2 is not going to happen. And so our tree is going to look like this, and we're losing all of those pieces of the tree. And if we wrote this out for F20, you'd see we're cutting out most of the tree. And pretty much what we have is just sort of come down this left branch and then go back up. So F40, we're going to do 80 calls, basically, to the Fibonacci function. All right, so let me give you the setup for PA5, and we'll go through the details tomorrow. So the basic area is something called the Knapsack Problem. So imagine that you go to the store. What store should we go to? Let's go to Best Buy. So you go to Best Buy and you walk in and alarms go off and lights start flashing and security rushes over and grabs you and says, "Congratulations, you're the 10 billionth customer at Best Buy. And we'd like to reward you by giving you a shopping spree." Okay, so this is a publicity thing that happens. I had a dream about it, but I won like a banana or something crazy like that. I was like, what? It was at Kroger. So you're going to go on a shopping spree. Okay, so here's what they do. They give you a bag. And this bag can hold, say, 20 pounds of stuff. And they say you can put anything you want in this bag up to 20 pounds, and it's yours. Don't have to pay for it, don't have to pay taxes, just free for you. 20 pounds of anything you want in the store. Okay? And the question is, what should you put in the bag, right? Because you're just going to go out and you're going to sell it all right away, so you're trying to maximize the dollar value of what's in your bag. And so what would you put in there? Would you fill your bag up with pens? Probably not, because 20 pounds worth of pens might cost, $50. Would you fill it up with 1 terabyte micro SD cards? Probably a good choice, because those are like $500 each, and 20 pounds of micro SD cards, that's going to be like 1 million cards, right? So you can make a lot of money like that. So the general question is, how do you decide what to put into your bag to maximize the value? Now, if you do this at Whole Foods, right, and they give you a bag and say you can take 20 pounds of stuff, you probably go to the bulk section, right, and you find they don't actually have this, but you find the bulk bin of saffron, right? So saffron, how much does saffron cost these days? Anybody know?
Like $20, right?
It's like $20 for like a micro ounce or something. I mean, it's the most expensive spice on the planet. And if you could get 20 pounds of that, right, that's like gold, So you would fill up your bag with as much of that as you could. Now, if they don't have an unlimited supply of saffron, if they only have 5 pounds, that takes 5 pounds. What do you put in next? Find the next most valuable thing, right? So maybe that's the gold-laced oatmeal that has like real gold flakes in it. And so you load up your bag with that, right? But you come up with some kind of algorithm for like, what should I put into my bag? And if you can put in fractional amounts of things, if it's like a bulk bin and I can just take as much of this stuff as I want, right, it's pretty easy. Find the most valuable item per pound, take as much of that as possible. And if you exhaust the supply, find the next most valuable thing per pound, take as much of that as possible. Okay? It gets harder when you're not allowed to do that. You're not allowed to take a quarter of a laptop, right? Your laptop weighs 7 pounds and you've only got 4 pounds left. You can't take 4/7 of the laptop, right? You either take a laptop or you don't take a laptop. So this is sometimes called the integral knapsack problem, where you can only take an integer amount of items. And we're going to talk about the unbounded variety, where there's an infinite supply of things. This is a great Best Buy. They have an infinite number of these micro SD cards. They have an infinite number of laptops. And so you can just say, give me 15 mice and 25 flash drives and 17 of these sunglasses. And so we want to talk about an algorithm for optimizing what you put into the bag, and it's called the knapsack problem. It's a classic problem in computer science. It's actually been worked into a crypto system because it's considered a hard problem, kind of like factoring primes. So the way we do RSA, there's a tweak on that actually comes from putting things into a knapsack like this. All right, so we'll look at algorithms for this tomorrow, and it's going to turn out that if we use dynamic programming, we can solve this problem pretty efficiently, and that's going to be PA5 in a nutshell.